Welcome to the Interfacing to Digital Potentiometers web presentation. We will cover material which should give you a better understanding of the different interfaces that are used to interface to digital potentiometers and some special features that Microchip supports on the serial interface. A digital potentiometer device has three main functional blocks. These are the serial interface, the system control, and the resistor network. Today we will be focusing on the serial interface. There are three common serial interfaces. These are a simple up-down interface, the SPI interface, and the I2C interface. The up-down interface is the simplest of the three interfaces. The wiper setting is only moved one position, either up or down, from the current position. This occurs on the rising edge of the up-down pin when the CS signal is active. This is okay for many applications. This includes when a non-volatile device is being used for calibration at the manufacturing step. The test hardware would monitor the appropriate resistor network node and send commands, increment or decrement, until the unit is calibrated to within specification. To go to a known wiper position, the controller must force the wiper to either the full scale or zero scale position. Then the controller must count the desired number of steps from the full scale or zero scale position. This figure highlights the starting state of the up-down pin when the CS pin goes active. This starting state determines if the rising edge of the up-down pin causes the wiper setting to increment or decrement. The SPI interface is also an easy interface. The device requires a minimum of 3 pins. These are the serial in pin, or SI, the serial clock pin, or SCK, and the chip select pin, or CS. The serial out pin, or SO, is not required to be implemented, but then the ability to read the contents of the device or to serial chain devices is lost. Digital potentiometers packaged in small pin-out packages, such as SOT23, do not have enough pins to offer the full serial interface and the resistor network terminal pins, so a trade-off will have to be taken. Each additional device on the SPI bus will require its own CS pin. The SPI interface can allow fast communications between the host controller and the digital potentiometer. The I2C interface adds some complexity to the host controller's firmware, but allows the interface to be as few as 2 pins while still being able to read and write the device. Multiple devices can easily be added to the bus, and due to the open drain output for the serial clock and data signals, all master devices can initiate serial communication. Address pins are used to differentiate multiple of the same devices being used on the I2C bus. The I2C bus also has better noise immunity than SPI or the up-down interface. Here is a comparison between the I2C and SPI interfaces. With respect to bus speed, SPI is much faster. This is because the common I2C bus rates are 100 kHz and 400 kHz, while SPI has a much faster bus rate. The I2C protocol recently added a specification for high-speed node with a 3.4 MHz bus rate, but at this time I'm not aware of any digital potentiometer devices that support this high-speed mode. With respect to the host controller firmware overhead, the I2C protocol is a much more involved protocol. This is due to features such as multi-master support, bus arbitration, clock stretching, the acknowledge bit, and other features. Supporting these features require much more host controller firmware and processing than the SPI protocol. With respect to I/O requirements, both the SPI and I2C can be done with 2 pins, but the SPI interface would not be at full functionality since the host controller would not be able to read the device, and the device would always be selected since the CS signal would need to be tied active. The I2C protocol only requires 2 signals. These are the SDA and SCL pins, and the address pins A0, A1, and A2 can be tied to the desired state, which could allow multiple devices on the bus. With respect to bus noise immunity, I2C was designed to address automotive applications which are noisy environments. The use of the open drain bus, data only changing when the S-clock pin is low, and some other characteristics makes the I2C bus less susceptible to bus noise. Microchip Technology's wiper lock technology allows the non-volatile wiper setting to be locked, that is, inhibited from being modified by normal commands. Normal commands are commands whose interface signals range from VIL to VIH. High voltage commands can be used to modify the wiper setting value or to lock and unlock the wiper protection. A high voltage command requires the chip select pin goes to VIHH instead of VIL for the command cycle, and VIHH has a minimum voltage of 8.5 volts. Wiper lock is useful in many applications, including manufacturing calibration, where the application system should not modify the calibrated wiper setting during operation. This would be used as a digital replacement for a mechanical pot. Wiper lock technology offers several benefits to the application circuit. Some of these benefits include the default wiper setting is protected from being corrupted by the host controller, so when the digital potentiometer has either a power on reset or brownout reset condition, the default wiper setting of the device will be loaded. Normally, once this value is set, the system forgets about this value. But this flexibility to reprogram the default wiper settings allows the system to be recalibrated as needed. This recalibration could be done to address the shift in characteristics of other system components during the servicing of the system. Recalibration could also be done to address an update of the application firmware, which may require a change to the default digital potentiometer wiper value. I want to thank you for spending your time with us today, and I hope you have enjoyed this presentation.